So this is the lesson on the product rule or the product law. Like all of the other rules of differentiation, you are not given the product rule, which you can think of as kind of a formula. You're not given any formulas or rules directly on any kind of data sheet. What we're going to be doing today is learning what the product rule is, and we're going to use it to determine derivatives. And then, of course, we're just going to continue to use derivatives for whatever we're asked to use them for. It's just that now we'll be able to differentiate more complicated functions. Very often in math, you encounter rules that connect two operations together that it turns out you don't really need a rule for. The order in which you apply the two operations doesn't change the outcome. Sometimes, however, the order in which you apply the outcomes does change, or apply the principles does change the outcome. So sometimes when two mathematical operations are performed one after the other, the result depends on the order in which they are applied. As an example, if I start with the number 8, and I'm going to perform two operations to it, and those of you that have taken 30-1, we're talking about a composite function here. We're talking about feeding in an input into one function and the output becomes the input for the second function. But if I take that 8 and I square it and then add 7, I get 71. You can confirm that. 8 squared is 64. 64 plus 7, I hope, is 71. But what if you start with the same number and you perform the two operations, that is to say, squaring and adding 7, but you reverse the order. You change the sequence in which they happen. Well, if I take 8 and add 7 first, I get 15, and when I square 15, I get 225. So clearly, squaring and adding are what I call order sensitive. There's a technical term for this, but it's used in multiple places in math, and it can easily confuse you. Okay, so I just say order sensitive. Operations are not order sensitive if the order in which they occur doesn't change the outcome. For example, multiplication and division. When you look at BEDMAS and it says brackets, exponents, and then it says division, multiplication, it could say multiplication and then division. It doesn't matter. Because if I take as an illustration 5 times 8 to get 40 and I divide 40 by 2, I get 20. If I take 5 divided by 2 to get 2.5 and I multiply 2.5 by 8, I still get 20. So we would say that multiplication and division as a group of operations performed one after the other are not order sensitive. There are many operations that are order sensitive and some that are not. For example, I'll give you another quick one. Order sensitive adding and squaring. Right? This is why I would get incredibly upset with you if you thought that this was x squared plus y squared. Right? If you add x and y and then square it, you get x squared plus 2xy plus y squared. Okay? There's an order here that changes the outcome. You can't just square each of them and then decide to add them together. On the other hand, if it was x times y, then it wouldn't really matter if you squared everything first and then multiplied them. So what we're determining in the warm-up here, everybody, is whether multiplication in sequence with differentiation is order sensitive or not. That is to say, if we're looking at the derivative of a product of functions, the derivative of f of x times g of x. So what are we differentiating? The product. And the derivative of f of x times the derivative of g of x, which is the product of the derivatives. What's on the left side is the derivative of a product. So you're multiplying first, then you're differentiating. What's on the right side is you're differentiating first, and then you're multiplying. Is that order sensitive or not? We're wondering if that's equal. I think intuitively speaking, you know it's not equal, otherwise why would we have some special rule? To use a simpler notation, f times g quantity prime compared to f prime g prime, are they equal? So understand what we're after here. Okay. So consider the functions f of x equals 3x and g of x equals x squared. In calculus, we can't get too much simpler than that. Determine each of the following. What is the derivative of the product of the functions? So when you take a look at this, which I'm going to rewrite a little larger, d dx of f of x times g of x, we have to multiply the functions first and then differentiate. So this is going to be the derivative with respect to x of 3x times x squared. And I'm using this opportunity to really get you used to the differential notation, the d dx notation. 3x times x squared is 3x cubed. And clearly we know how to differentiate that, because that is a very basic power times a coefficient. You bring the exponent down in front, you get 9, drop 1 from the exponent, so it's 9x squared. Are we fine with that? So in this particular case, the derivative of the product is 9x squared. I'm going to actually write this down. Whether you decide to or not is up to you. This is the derivative of the product. In other words, the order of events is you're multiplying and then you're differentiating, and that's what you get, 9x squared. Calculate or determine the product of the derivative. So this is different. This is saying take the derivative with respect to x of f of x and multiply by the derivative with respect to x of g of x. And those brackets are not needed. I just wanted to emphasize up top here that we're multiplying derivatives. So if you want to put the brackets in, have at her. It doesn't really matter. Well, f of x is 3x. So rather than me saying find the derivative of 3x, I'm just saying d dx of 3x. That's what that means. It means take the derivative of 3x. And then g of x, so we're going to multiply that by the derivative of g of x, which is x squared. Well, we can do that. The derivative of 3x is 3 with respect to x. The derivative of x squared is 2x. So we are getting a derivative of 6x, and this is the product. And you know what? I guess I just misspoke. I said we're getting a derivative. No, we're not. We're getting a product of 6x. This is the product of the derivatives. And there's this word in math which is called a counterexample. If you were asked to determine if something is false, all you need to do is find one counterexample to that statement. So given that in this particular case, and you'll have to maybe help me out here, the derivative of our product was 9x squared, and the derivative of f of x times the derivative of g of x, in other words, the product of the derivatives was 6x, if we find one example where they're not equal, then we have no business saying they're equal. We can't say they're equal unless they're always equal. That's what rules are about in math. Bottom line is the derivative of a product and the product of a derivative are not the same. So what can we conclude? I'll use the lazy person's notation here, which is that. I think you get my drift there, right? What I'm telling you. So how is it we do find the derivative of a product without actually multiplying the stuff through? Well, before I get to that, I want to point out to you that many of the examples today, you could multiply them through. In fact, I just want to show this to you. If I ask you to find dy dx if y is equal to 3x minus 2 times 4 minus 3x, I suppose if you don't know the product rule, and you don't right now, you'd have to multiply it through. And we've had examples like that before, where you have to FOIL things out or you have to make them work with the power rule. So you could differentiate this without the product rule, but that would involve multiplying it out. Are you with me? Okay. Well, could you find the derivative of this now without using the product rule? Yeah. Then you'd have to multiply it out, and given that our derivatives need to be in factored form, you're going to get some degree 13 polynomial, which when you differentiate will give you a degree 12 polynomial, which you will then have to factor, which you could with the factor theorem that we learned this morning in Math 30-1, but you'd have to do synthetic division 10 times to get it down to a quadratic. So there is going to come a time where the product rule is absolutely, without a doubt, necessary. So what is the product rule? Let me show it to you first. So the derivative of a product of two functions can be found using the following rule. I think I've got time today, and I will show you the proof of it. We'll talk about how you can prove it, because I think when you get to post-secondary, it would be something you would be expected to do. The product rule is like a rhythmic kind of thing. The derivative of a product of two things is the derivative of the first times the second plus the first times the derivative of the second. Okay. The derivative of a times b is the derivative of a times b plus a times the derivative of b. For whatever reason, I don't know, this author has chosen in this version of the textbook to write the product rule this way. In other words, they've taken those two terms, f prime g and fg prime, and switched the order of them. You understand that mathematically they're the same. At times, I've seen the author do this. But since the order in which you multiply two things together doesn't change things, and since the order in which you add two things together, there's all kinds of ways you could write this. I just prefer with what is in most textbooks and what I learned it as. The derivative of the first times the second plus the first times the derivative of the second. If you want different notation, I think this is hugely clunky. Like, this is just nightmarish in terms of the complexity. You could use this notation, which is almost worse. I want you to notice with this bottom notation, it's g of x times the derivative of f of x plus f of x times the derivative of g of x, only because, for example, if you write something like this with the derivative of f of x first, and then you go times g of x, it's a little ambiguous as to what you're differentiating there. Is it just f of x, or is it f of x times g of x? Anyway, that's the rule. The derivative of a product of two functions of x is the derivative of the first times the second plus the first times the derivative of the second. So I'm going to show you a proof. And Gottfried Leibniz came up with a very elegant proof. He was the first one to discover the product rule in, I want to say, the late 1700s, I think. But it requires the use of something called infinitesimals, which is beyond the scope of what we've learned so far. So what we're going to do to prove this is we are going to prove it using the definition of a limit, or definition of a derivative. But it's going to be slightly altered, because normally what we do is we say, and I want to write this down elsewhere, and don't write it down, I just want to bring this up to remind you, that if you have f of x, then the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. That shouldn't be a big surprise to you, right? You've seen that a dozen times. The issue is we're not trying to find the derivative of f of x, we're trying to find the derivative of f of x times g of x. So you're going to have to watch very carefully with this first step. Our function, I just want to make a note of what the function is here, is actually the product of two other functions. And it's really unfortunate that we always use f and g, because f is the sole function in this limit definition, right? But you have to get your head around that, and it's not a big deal. I like how when I said that, some of you just kind of went, so what? So what will this be equal to? The derivative, and I'm going to choose to write it as dy dx so as not to confuse the issue with our different f's and g's, will be the limit as h is approaching 0 of f of x plus h g of x plus h. Because the function is f of x times g of x, we need to evaluate that whole function at x plus h, minus the function, which is f of x g of x. But we're going to leave a big gap in between these. I'm going to leave it as big as I possibly can and still write f of x g of x. Now, why are we leaving this gap? Well, I've done research over the years trying to determine who first cracked this puzzle. Because as it stands right now, there's nothing you can do with that. And this is the weird thing about proofs. We're trying to turn this into something useful, and it seems so abstract that it can't go anywhere. And I've never been able to find out who did this. Leibniz didn't. I've looked at textbooks from the 1920s. It's the proof that they have, but I can't figure out who. Somebody came up with it. Somebody played around with this long enough, and they said, you know what? It turns out if I do this, if I subtract f of x, g of x plus h, and then immediately add f of x, g of x plus h, boy, my spacing was just perfect, then it's still the original expression. Because this is equal to 0. So now what we're going to do, we're going to break this into two fractions. This is all over h, but I can write the limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x, g of x plus h over h, plus f of x, g of x plus h, minus f of x, g of x over h. In other words, I'm tearing it apart into two fractions. They will both still be over h. So I'm going to have f of x plus h, g of x plus h, minus f of x, g of x plus h, and this is over h, plus I'm going to have f of x, g of x plus h, minus f of x, g of x over h. Are you with me? All I have done is I've said this. I mean, I don't think you would want to include those diagrams in a proof, but I'm trying to explain to you what I've done. Now, at some point here, many of you are going to start to see where this is going. But there was a time when we first learned about limits, everybody, that I told you we would need to know properties of limits to do proofs, and this is one. The fact of the matter is, unlike derivatives, no, sorry, just like derivatives, the limit of a sum is the sum of the limits. So rather than me saying the limit of this beast plus this beast, I can say the limit of the first beast plus the limit of the second. And that's the next step. So this becomes the limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x, g of x plus h, over h, plus the limit as h approaches 0 of f of x, g of x plus h, minus f of x, g of x, over h. Okay? I know as a student of math, you expect to be taught this is the series of steps you do to do the math. But we're getting into an area right now where if you had to prove something, it isn't entirely obvious what you're doing or why you're doing it. So we're standing on the shoulders of people before us who have figured this stuff out. Okay? Now, it turns out that for each of these, there's a common factor in the numerator. I can factor out a g of x plus h out of the first and get the following. And I'm choosing to be a little sneaky about this by taking that g of x plus h and not doing this, but instead just separating it from the other part. And I think some of you might see where things are starting to congeal here. Because this, taken as a limit, is the derivative of f of x. The derivative of f of x is f of x plus h minus f of x all over h taken as a limit when h approaches 0. We can also factor out of this limit argument an f of x and have left g of x plus h minus g of x. And it might be to some of you maybe, it might be that we're done the proof, but we're not. We still have a ways to go. How many of you, though, can see the product rule embedded in there? We're getting there. There's another property of limits. Unlike derivatives, the product of a derivative is not the same as the derivative of a product. However, that is true for limits. This is saying the limit of a product of two things is equal to the product of the limits of those two things. So what I can do now is rather than saying the limit as h approaches 0 of a times b, I can say the limit of a times the limit of b. And this becomes the limit as h approaches 0 of g of x plus h multiplied by the limit as h approaches 0 of f of x plus h minus f of x over h plus the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x over h. How many of you see that it's almost the product rule right now? It's not quite. There's something that we got to clean up. Like this second part is perfect because you would make the argument, this first part rather is perfect. that you evaluate this limit by putting h equals 0 right there. Well, what does this become? It becomes g of x. This is the definition of the derivative of f of x. Right? That's the meaning of the derivative. The limit as h approaches 0 of the function at x plus h minus the function at x all over h. Plus, there's a plus here, this is clearly g prime of x. How does this become f of x, which would complete the product rule? Well, since f of x doesn't depend on h, it doesn't matter what h is doing. It's almost as if f of x is a constant compared to h. So if I say as h approaches 0, what is x squared doing? It's x squared. In this case, it's f of x. So what we've done is we've proven now by just reordering this to suit my needs or my desires, because I like it this way. The derivative of the product of f times g is the derivative of f times g plus f times the derivative of g. So that's a proof if you ever need it. What we really are interested in here is putting this together. So what is the derivative of this function? What is dy dx? I'm going to write out something, and I suppose I want you to write it down too, but it's something that in the course of your work on paper you wouldn't do. I've seen profs that are adamant that you do this. I don't think it's necessary. Dy dx is this. I used to think this would confuse students, but I think it is an important thing to look at. What I've written down is what the product rule says we need to do. This I'm not really happy with how I've lined things up, but that's okay. This is the derivative of the first. Do not use this notation. This is just me teaching. This is the second, this is the first, and this is the derivative of the second. Right? I'm just communicating what it is we're doing. In all reality, you would probably just say, looking at the very top, the derivative of the first is 3 times the second, plus the first is 3x minus 2, times the derivative of the second. We want things to be simplified and preferably factored, but since when we inspect this it's all linear, it's not even going to be quadratic, factoring doesn't really have a place here. Let's multiply this out and simplify it. Then I suppose if there's something to factor, we can. Look at that, 12 minus 9x minus 9x plus 6. If you had me for math this morning, you'll know that my brain is not operating well with multiplying numbers today for some reason, or adding them for that matter. Can you confirm that I've expanded that out correctly? Okay, so what we get is negative 18x plus 18. Which, had I thought about it a little bit more, I would have written 18 minus 18x, but it doesn't really matter. If you want, you can factor the 18 out or a negative 18 out, but that's not what we're here to talk about today. Any questions with that first example? Okay, g of u is equal to 2 root u times 3u squared minus 2u minus 3 find g prime of u. So let me rewrite this first of all. And again, I want to go back to something that I mentioned earlier on today. I think if you just had your choice on how to find the derivative here, you'd be crazy not to multiply that 2u to the half in. And you know, dispense with the product rule. But if it were that, well, you can't multiply that 2u to the half through unless you multiply it through to one of those 12 factors and then expand out everything. And then you're just asking for trouble. So we have to use the product rule. So g prime of u is the derivative of the first. Just take a pause for a second there. The derivative of 2u to the half is u to the negative half. Swing the exponent down, drop 1 from the exponent, times the second. Plus the first, times the derivative of the second. We okay with that? We want to simplify this. I mentioned earlier factoring is the way to go. The simple fact of the matter is you have two terms here. So when we simplify this, we want to consider what we can factor out of the terms. And there is a factor of u to the negative half in that first term, and there is also a factor of u to the negative half in the second term. I mean, there's a factor of 2 and a u to the 1/2, but u to the negative 1/2 is a factor of u to the half. We take out the lowest exponent on u. What do we have left? Well, out of the first term, we have the 3u squared minus 2u minus 3. Plus, out of the second term, we have that 2. And we are also going to have u to the 1. Because u to the 1, which we have left, times u to the negative half, which we factored out, would give u to the 1/2, which we started with. And then I also have 6u minus 2. Given that now everything I'm underlining here, given that there is no common factor between all of this mess, we're at the stage where we just multiply it out and see what happens. The u to the negative half that's over here can go on the bottom. So we end up with something over u to the half. And I have, you can do this in stages if you like, but I have 3u squared. And then I also have plus 12u squared. I get 15u squared, assuming 3 plus 12 is 15. I have negative 2u, and then I have minus 4u. So I get negative 6u. And then I have minus 3. Double check that. 12 and 3 is 15u squared. Negative 2 and negative 4 is negative 6, and I got that orphaned negative 3 there. I can certainly factor a 3 out of this. You might wonder what the big deal is. Well, you just need things to be factored. Let's take a minute and talk about the question that I think Christian had asked about, where we were trying to show that there were no points where the slope of a tangent was 3. You guys are with me on that? What if instead I said, looking at this function, and you can change all those u's to x's if you like, What if I asked you on that function, where are the tangents or tangent horizontal? Well, that means a slope of 0. So I'm asking you what value of u makes the derivative 0. But look, if you look right here, and I said, go ahead and tell me what value of u makes that 0, you can't do it. If you look here, you can't do it. If you look here, you can. Because then you're talking about where is 5u squared minus 2u minus 1, 0. By the way, is that factorable? I'd be blown away if it is. Can we do the b squared minus 4ac thing? Please. No, you're going to get 24. It's not factorable. But it is solvable. There are places on this function where the tangent has a slope of 0. There is also a place on the function. So there's places where the derivative equals 0, and they would be the solutions to that. There also is a place where the derivative is undefined, and that can have a lot of useful applications. I know you tend to think if something's undefined, it's just meaningless. That's not true. If something's undefined, it can have a meaning, a useful one. So this is why we want to get things in factored form. Any questions with that one? All right. What's the equation of the tangent to this function at x equals 2? So you need to determine, the coordinates of a point, and I'm going to give you a minute to find the y coordinate. You're going to put 2 in for x. I don't care how you do it. Calculator, head, tables, functions, I don't care. But I would like you to find the y coordinate. I'll do the same thing, and then we'll see if I was able to get the right answer. I'm getting negative 80, and I see a few people nodding. At least one, I think, did it on a calculator, so we're all good. Okay. We also need to know the slope. What's the slope equal to? The slope will be equal to the derivative of the function at x equals 2. That's how we communicate at x equals 2, and I think I've shown you that before. So we need the derivative. Piece of cake. dy dx is equal to the derivative of the first times the second plus the first. I'm just going to move this stuff out of my way. You probably have more room on paper than I have up here. So derivative of the first times the second plus the first times the derivative of the second I'm just having a really hard time focusing today. That looks okay though, right? Okay. Listen, you have to work smarter, not harder. Don't think you have to multiply this out. Why are we finding the derivative? So we can find the slope. Well, why not just put 2 in here? If you put 2 in here, and I'm not going to show every little bit of work, but if I put 2 in for x everywhere, I can figure out what these pieces are. Six times 2 is 12, minus 2 is 10. I already figured this out. I believe this was negative 10. I figured that out as part of finding y. I think I also figured this out. This is 8. So I'm just putting 2 in for x. Negative 11. 8 looks like he's had a few too many drinks and he's kind of leaning a bit there, but you get the idea. So now we have to figure that out. That's negative 188, I think. I'm pretty sure. And no matter how many years I teach this, I make it's not a mistake. It's something that I think if somebody watched this they'd go, oh man, that's not true. And they're right. dy dx is not equal to negative 188. dy dx is equal to this. This is dy dx at x equals 2. Right? If we want, I was going to say, if we want to be technical, but that sounds as if we don't have to be. We need to be technical. It's math. It's calculus. It's a technical science. So now we have the point that the tangent line passes through, because that's the point of tangency, and we also have the slope. It's candy stealing territory. Y minus y1 equals the slope times x minus x1, and we can leave it there. I don't think we need to spend class time rearranging that as ax plus by plus c equals 0. Are we okay with that example? All right. Determine the slope of the tangent to this function at x equals 1. So we need to know the derivative. Well, just lay your pencils down for a second and just observe. It's a product of three things. And whether I write A, B, C here or not, I think you get the drift. I am interested in knowing what's the derivative with respect to x of the product of three things. I don't have a product rule for the product of three things. I have a product rule for the product of two things. Well, let's make this the product of two things. Right? I know how to find the derivative of this. It's going to be the derivative with respect to x of AB multiplied by c. So I'm taking the derivative of the first times the second plus the first times the derivative of the second. However, this is something we know how to differentiate because it's the derivative of a product. So now I have the derivative with respect to x of A times B plus A times the derivative with respect to x of B. So this part that I've just written is that blue part. And now I need to multiply it by c, and I better make sure I multiply the entire thing by c. This is going somewhere. You're going to see a pattern that emerges here. And the pattern is going to extend to 3 factors or 4 or 5. And then I have plus AB dc dx. When I expand this out by multiplying the c through, I get the following. The derivative of A with respect to x times B times c. And I'm just going to put the brackets there to make sure you understand. It's dA dx, not dABC dx. Plus A dB dx c plus A B dc dx. You can prove this using the binomial theorem, it turns out. Of those 3 factors, you have to choose each one once to differentiate while you leave the others alone. So it's the derivative of the first times the other 2, plus the derivative of the second times the other 2, plus the derivative of the third times the other 2. And if it were A, B, C, D, it would be the derivative of A times BCD, plus the derivative of B times ACD, plus the derivative of C times ABD. How am I doing? Plus the derivative of D times ABC. So when you see it in that light, it is not a difficult question. And I suppose I'm asking you to maybe keep that stored somewhere in the back of your brain in case you ever can make use of it. So dy dx, now we're writing again, is the derivative of the first, 8x cubed, times the other two, and you better believe you have to be checking things here. Plus, I can tell I'm not going to have enough room, so I'm just going to stack them. The first times the derivative of the second times the third plus the first times the second times the derivative of the third, and I'm going to step back and check all three of those big pieces. 8x cubed, second, third. First, negative 15x to the 4, third, first, second, derivative of the third is 2. We're good? I'm just in teaching mode here, and I want to just fit this on one screen. What you need to do, and I didn't make this difficult because of the complexity of this, I'm using x equals 1. So you need to put 1 here, here, and here and figure out what these three multiplied together will be. It will be 8 times 1 times negative 3. I think it's negative 24. But I need somebody else to confirm that that's what you're going to get. And then we do the same thing with the middle piece here. We get negative 1 times negative 15 is 15 times negative 3 is negative 45. And again, don't just nod. Double check this internally in your brain or on a calculator that you get negative 45. This morning in math, I said, so is that number okay? And I saw a whole bunch of people nod, and we finished most of the problem, and it wasn't right. So don't just nod, make sure it's right. Is it negative 45? Now you're afraid to nod, eh? This is negative 1. I'm putting 1 in. Negative 15 is 15. This is negative 3, sure, negative 45. And the last one will be negative 1 times 2, which will give you negative 2. We're adding all of these together, so what do we get? 69, negative 71 is the slope of the tangent to that beast at x equals 1. As I said, with the product rule, the way this textbook is organized, and I'm not critical of it, I like the way it's organized. I like doing the product rule before something else. But because we're doing it before this other thing that I don't want to talk about, that we will get to, almost every question, you don't need to use the product rule. You could expand it out. But later you will not be able to. Tomorrow we're going to be looking at the quotient rule, and then we're going to be looking at that other thing that ties everything together, which it turns out is called the chain rule. So here is a list of problems that you can practice for the product rule.